So sensation is the stimulation of the sensory organs. So our senses have different sensory organs that we use to sense and receive sensory input. So for the visual system, it's photoreceptors in the retina. For the auditory system, it's mechanoreceptors in the cochlea. And for the olfactory sense, it's these chemoreceptors that pick up chemical senses in the air. And this is opposed to perception, which is the selection, organization, and interpretation of that sensory input. So when we look at a fire, we feel the heat, we can smell the smoke, we can see the light, and that's sensation. But our brain puts this all together and tells us that this is a fire. So we get one form instead of all the different senses. So to begin, we need to talk about the anatomy of the eye. So there are some very important structures and then some other structures that I'm not really going to cover. But for one, the lens. So the lens is the outer part of the eye, and what this does is it focuses light, and it can either flatten out if you're trying to focus on something that's far away, or it can kind of round out, and that's for if you're looking at something a little bit closer. So the textbook, I think, calls it flattens versus spattens. So that may be a good way to remember it. So the pupil, which is the dark spot in your eye, this will regulate the amount of light that's coming in and hitting your retina. So this can constrict, which would let less light in, but you'd have a sharper image. But it can also dilate, which is when it opens up. And this will give you more light, but at the cost of that sharpness. So in bright light, the pupil will constrict because it already has enough light to work with, and it doesn't need to be gathering as much as possible. But in dim light, it's going to dilate to catch as much light as possible to give you the best image on your retina. If I start going too fast, just slow me down. You guys need to take the notes. So when the light gets through your pupils and hits the back of your retina, there's some important structures there as well. So to begin with, the retina is a thin layer of cells on the back of your eye that absorbs that light, processes the image, and then sends the information away to the brain to be organized and understood. So the optic disc is your blind spot. So you have a blind spot where all of the nerves leave the back of the eye, where there is no retina. So you probably have heard about this. There's a blind spot in each eye, and you can actually sometimes see that if you can hold something close enough, like a piece of paper with two dots on it, to your face. You can kind of see that if it's close enough to you, but our brain automatically kind of corrects for this, and that's why we really don't see it too often. And so also on the retina are these specialized receptor cells, specifically the rods and the cones. So the rods are more sensitive to light, and they're located across the retina. So we have about 100 million rods. And they're located across the retina, but they're also found a lot in the periphery. So they kind of take care of our peripheral vision. And we also have the cones. So the cones are receptive to color. And these are located mostly on the fovea. The fovea is a spot at the back of your eye. And we only have 6 million of these, which is why we aren't really as good at determining different colors. But let me say that again. The cones are receptive to color and are found mostly on the fovea. So make sure we're writing that down. Now the cones are not as receptive to light, so they take care of most of our daytime vision. So whenever we're looking during the day and perceiving images during the day, it's mostly our cones doing the work because the rods are so sensitive to light that it would kind of overpower. So the rods are more important for our nighttime vision when we don't have as much light to work with. So we need our rods there to try to catch that light. So let me say that again. The cones are responsible for daytime vision. The rods are responsible for nighttime vision. Let's make sure we write that down. Any questions about any of this? So once it hits the retina and then leaves through the optic nerves, there are a few pathways that information will take in the brain. So it leaves the eye through those axons in the back called the optic nerves. It's going to travel through the optic chiasm, which is this spot here where they cross. And this is going to send the information from each eye into opposite hemispheres. So the information from the right visual field will go to the left hemisphere, and the information from the left will go to the right. So this just makes sure that both hemispheres of the brain are getting all of the information from both sides of the eye to create the best image. Now once it gets to the optic chiasm, it has two different pathways that it can take. So there's the main pathway, and then there's a secondary pathway. So the main pathway, it projects onto the thalamus, and it will synapse into the lateral geniculate nucleus, which is just normally called the LGN. And then that information can be processed there, and then it's sent to the occipital lobe, which is at the back here. So the occipital lobe has your primary visual cortex. It's where a lot of your visual information is processed. Now the second pathway will lead to the midbrain, and then it will go through the thalamus and to the occipital lobe. However, in the second pathway, it doesn't hit all the same spots, even in the thalamus and the occipital lobe. And right now we think that the reason for this second pathway is for the coordination of visual input with your other senses, so sight or smell and hearing and things like that. So once that information reaches the primary visual cortex in the occipital lobe, additional processing is often needed to determine either what you're looking at or where that object is. So specifically with things like tracking, if I wanted to grab my water, I would have to know where that is to be able to target that. So we have two different pathways that are pretty important, and these are called the what and the where pathways. And these are the pathways that the information goes to be processed. So the what pathway is the ventral stream, and this, as you can see down here, goes through the temporal lobe, and this is really responsible for color and form, so detecting what exactly we're looking at. And psychologists have found face detection specialized cells. So these are cells specifically evolved to detect faces in humans and monkeys. Now opposed to that is the where pathway, which is also known as the dorsal stream, which goes to the parietal lobe. And this is really important for motion and depth. So being able to see how far away your target is to be able to get to it. So when it comes to color vision, there's basically two theories that are most important. So the first one is the trichromatic theory. So this essentially posits that there are three types of receptors for different wavelengths of color, specifically red, green, and blue. And then our eyes will mix these colors to create the true colors that we're looking at, and this is called additive mixing. So for color individuals who are colorblind, most of these people are dichromats, which means that they just have to get by with two different types of receptors, and there's three types, one for each missing receptor type. There are some phenomena that trichromatic theory cannot explain. So let's look at one of these phenomena. Okay, so if you look at this American flag, there's a white dot in the middle. So stare directly at that white dot. Right, so did you guys see it? Right, so you should be able to see, red, white, and blue American flag. So what this is an after image. So after images are visual stimuli that appear after that original stimulus is removed. And it's made up of the complementary colors of the original stimulus. So obviously trichromatic theory can't explain why this happens, because you should just be looking for red, green, and blue. But when you get that white background after the image, now you're getting the complementary colors of what you initially saw. So a theory to explain this is called opponent process theory. So opponent process theory essentially posits that color perception depends on these receptors making comparative judgments between three different colors: red versus green, yellow versus blue, and black versus white. And that's what we see whenever we're looking at the American flag after image. Now, these two theories have been argued over and debated over a lot. You have proponents from both sides saying that this is the way, this is the way. But really, both theories have been shown to be correct. So it's been proven that the trichromatic theory is supported because there are three types of cones in each eye. There's the shortwave cones, the middle wave cones, and the long wave cones. And these respond specifically to red, green, and blue. However, the opponent process theory has also been proven because it's been found that there are specialized cells in the retina, the thalamus, and the visual cortex that will respond in opposite ways to red versus green and blue versus yellow. Specifically, these cells will either excite or be inhibited whenever they're exposed to these opposing colors. Okay, so now we've kind of covered sensation, so we can talk about perception. So I think perception is a little bit more interesting because perception can be so biased depending on how we or our knowledge about the world. So perception itself is the process in which the brain selects and organizes certain information from your senses to allow us to understand what we're seeing, hearing, smelling, touching, tasting. Specifically, there's two types of ways of looking at perception: top-down versus bottom-up. So top-down is when you use your knowledge that you already have about the world to make sense of what you're sensing. So whatever comes in gets kind of filtered through that knowledge that you already have, and then that determines what you make of it. And this is opposed to bottom-up, which is whenever you look at specific features of the stimulus to make sense of it. So if we look at this figure at the bottom, we can see on the left we have A and C, and then on the right we have 12 and 14. So in the middle we have the same figure, right? But because of the context that we're given, on the left side we either see B, and on the right side we either see 13. If we were to take away that context, we would probably go to a more bottom-up style of processing because we would only be looking at those features and we'd have to engage in some feature detection. So top-down processing is affected through your experiences, your culture, your personality. All these types of things can affect how you see the world and how someone else can view the same thing and get a different idea about what you're looking at. So most of the time we're engaging in top-down processing because most of the time we already have some information about whatever it is that we're looking at. It's very rarely that we only use bottom-up processing. So for form perception, we have this figure and ground. Specifically, we tend to assign the figure, which is object in the front or the foreground, to one shade or color while assigning the ground or the background, the backdrop, to another. So this is a common illusion that you'll see where you can kind of shift back and forth between kind of like the chalice in the middle and then the faces on the right. So I'm sure you guys have probably seen this before. So we also have different ways of grouping images and figures and elements, and we kind of group them up because of different principles, and these are called the Gestalt principles. So the first one, proximity, we basically, when we look at these circles, we see that these go together because they're closer together. So proximity, they're closer together. Similarity, we see that these are similar, and you have the shaded versus the unshaded ones. Continuity, whenever we look at this image here, we don't see four small lines, right? We see two lines intersecting each other because our brain wants to continue on. Closure, this is, we can all see the triangle here, even though it's actually not there, right? What our brain wants to do is close these gaps, and this is called the closure principle. So let me say that again. Right, with the closure principle, right, we want to fill in those gaps. Make sure we write that down. All right, the area, right, whenever we see it, we're looking at that small square. And symmetry, we're not seeing, a cutout here. Right, we're seeing two squares that have been overlaid. Right, our brain wants to make things simple and neat. And this is kind of some ways that we have found that we do that. Any questions about any of these? Okay, so when it comes to depth perception, we have basically two different types of cues. So there's the binocular cues, and then there's the monocular cues. So the binocular cues require both of our eyes. And one good example is retinal disparity. So retinal disparity is this idea that images that are closer to you, or objects that are closer to you, are hitting your retinas in different ways, depending on the convergence or divergence of your eyes. So if something is pretty far away, your eyes are tracking into that object, and you shouldn't have to experience much retinal disparity. It really only happens whenever objects are about 25 feet or less, and that's whenever they start hitting your retinas at different spots. So there is a demonstration of this. It looks stupid, but we'll all look stupid together, okay? So if you take your fingers and you put them about ½ inch apart, and you put it about a few inches in front of your nose, you should start to see like one finger right in the middle. Is it happening for anyone? You may have to kind of get closer or further away, but you don't want them too far apart. Anyone there? No? Yeah? So that's retinal disparity. So what's happening is essentially, as it gets closer to your eyes, it's hitting your retinas in different spots because one is probably going to be over or the other. And essentially what you see is a different figure depending on which eye is stuck in the retina, or which eye is hitting the retina and which part. But this is retinal disparity. So for monocular cues, these are cues that rely on basically one eye or the other. And these are also known as pictorial cues. And if you are in art or taking any art classes, you'll probably already know a lot of these because they're used in art to give depth to the images. So we'll go through these. So with linear perspective, this is something that's really used in artworks a lot because it draws your eye across. So you can see how we've got a linear perspective in that architecture there, and also coming back from the side as well. Occlusion is when an object is hidden partially or completely by another. So you can see the tree behind there, and also back in the back here. So height in the plane, as we can see, objects that are closer to us are going to be lower, right? And then objects that are much further away should be at the top of the plane. So light and shadow, pretty obvious, So relative or familiar size. So basically objects that get further away begin to look smaller, right? And we know that that pillar isn't going to be that small, right? We use that to detect distance. So instead of saying, oh, that pillar is really small, we say that pillar is really far away as opposed to the tree in the front here. So the text gradient here, or texture gradient, as we can see, as objects get further away, we begin to lose the texture, the details about that object. So the leaves in the front, we would have a much better kind of detail-oriented view of them as opposed to the ones in the back, And as you start to get even further away, if you see, a mountain with a lot of trees on it, you just kind of see a sea of green. and you really can't tell where any of the leaves are. But an object, a tree that's really close to you, you're able to see those individual leaves and probably even details about them. So this proximity luminance covariance, basically objects that are closer to us look brighter, and objects that are further away are a bit more dim. And this is dependent on illumination, of course, but that's just the essential kind of idea of it. And then again, aerial perspective, as it gets up or down, depending on how close it is, you're going to get a different view of it depending on its height. So perceptual constancies, some features are held constant even as your sensory input changes. So if you see someone that's really far away and they begin to walk towards you, they begin to get bigger, right? And they're not growing, they're getting closer to you. However, we can kind of play around with this a little bit. So for color constancy, whenever we see the image on the left, those two checkerboard squares appear to be different colors. But whenever we actually see, this is just because the illumination is messing with us, they're actually the same color as we can see on the image on the right. So this is just an illusion. So basically, this is going to be a task video. So you want to complete this, but there's going to be some distractions. So try to focus on the task.
Are you tired of pretzels not being Pop-Tarts, toaster pastries? Are you struck? The monkey business illusion. Count how many times the players wearing white pass the ball. Correct.
Anybody get it? Nice.
The answer is 16 tasks. Did you spot the gorilla? For people who haven't seen or heard about a video like this before, about half missed the gorilla. If you knew about the gorilla, you probably saw it. But did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold.
Okay, did anyone notice all of the changes? So how many of you had heard about the invisible gorilla, or at least that video before? Right, so quite a few. So the invisible gorilla video is a stimulus that was used in Simon and Chabris' 1999 study. It's called Gorillas in Our Midst. So a really interesting paper about inattentional blindness, which is what this is. So when he released that in 1999, it became very famous. And so now lots of students have already heard of it and have already seen the actual video themselves. So in 2010, Simon's created this new video which shows that whenever you're expecting something to happen, like the gorilla, now your focus is not on the basketball players, but now it's on this gorilla that's supposed to appear, and you're still going to miss things because now you're focusing on something new. So this is called inattentional blindness, and essentially it's the failure to perceive objects or events, no matter how salient they are, because you don't have enough attentional resources to be able to perceive that object. So you are sensing the gorilla. You're staring right at it, right when it walks through. You're seeing the color change, and you're seeing the basketball player exit the frame. However, you aren't perceiving it because your brain doesn't have the attention to be able to notice it. Now, maybe some of you did notice it all, and maybe none of us did. And these are really important questions that we need to answer about inattentional blindness. But essentially, we have a limited attentional capacity or bandwidth that we can use to pay attention. So we have to selectively focus our attention on different objects, events, or tasks. And whenever we have to divide our attention, we can miss events, or details. And our performance overall on whatever task we're doing is going to fall. So the Simon and Chabris study introduced the famous invisible gorilla stimulus in 1999. So the stimulus in Simon and Chabris' 1999 study was the invisible gorilla. So the question that researchers have been asking is, what influences this? Because obviously some people notice it, some people don't. And as psychologists, we want to know the individual differences or the context of the task itself that can influence this. So one thing that we found is age. Older adults are more likely to experience inattentional blindness. And this can be really scary when we think about older adults driving, right? Or any individual who's more likely to be susceptible to inattentional blindness driving. Because look but fail to see crashes are very common, in which someone looks but doesn't see the oncoming traffic. And a lot of the times, studies have shown that it's motorcycles that are most ignored or you're most inattentionally blind to. Also, alcohol consumption. Intoxicated individuals are more likely to experience inattentional blindness. In this study, they told some participants that what they were drinking was a placebo and others that it was alcohol. No matter what they told them, the intoxicated individuals were more likely to miss the event. So the perceptual load. Perceptual load is the amount of details in the environment that you're having to pay attention to. So the higher the load, the more likely it is for you to experience inattentional blindness. And mental load. So more tasks result in a higher likelihood of inattentional blindness. And again, we talked about this. Whenever you're having to split your attention between tasks, inattentional blindness can happen. So what about individual differences or cognitive differences? IQ, these types of things. Well, we don't really know. Maybe, and maybe not. There's not great evidence to support either side. And this is a debate that's kind of happening now. So obviously this is a really exciting topic. So some more examples of inattentional blindness, stimulus, and related concepts. So these are some stimuli that have been used before in the literature as unexpected events. So R. Hyman used a unicycling clown that individuals missed, a physical altercation between two men. So in this study, a participant was asked to jog after a Confederate. Do we know Confederate? A Confederate is someone who's in the study, right? They're the research assistant. So a participant was asked to jog after the Confederate and to count how many times the Confederate patted the head. And while they ran on this route, about 20 feet to the left, two more Confederates got into a fight, kind of like a wrestling match or something, I don't know. And most participants missed it because they were so focused on counting the pats. And also money hanging from trees. So this is a funny one. People walked through these trees that were overhead, and Dr. Hyman had hung money just hanging down from the trees. And they saw that individuals who were on their phone or talking were the most likely to miss that money hanging down from the trees. Also, what's probably happening here are money's green, leaves are green, and they're probably getting it mixed up there. So a related concept is change blindness. So change blindness is whenever you fail to notice a small change from one screen to the next. So this is most often seen in human factors or user experience. Whenever you want to show something to your user and you change something about the scene and they fail to notice that because it's not salient enough. So the best way to fix this is to either make it more salient or to provide multimodal feedback. So now we know that our phones are giving us haptic feedback as well as notifications. And these are good ways to address that. Also, inattentional deafness. So this is the failure to hear distinct sounds due to a lack of attention. Same thing as inattentional blindness, but this is for the auditory system. So one interesting study actually used the sound of nails on a chalkboard, in which about half the participants didn't hear because they're engaged in a secondary task. So this is why it's so scary, because we can miss all of this stuff and have no idea. So there's also this idea called the illusory of attention, which is whenever you show someone an inattentional blindness video and then you show them what they missed, they are very shocked, right? We have this idea that we pay great attention to what's around us, but oftentimes we miss stuff that's very important because we don't have the attention there. Another concept is this idea of multimodal inattentional blindness. So it's been shown before in studies that listening to the radio while you drive can cause you to be more likely to miss an unexpected event. And this really scares me for some reason, because this can happen almost at any time. And so, yeah, this is something I'm really passionate about. Do you guys have any questions about inattentional blindness or anything like that? I find it so interesting. So, any questions at all? Short lecture. You guys are welcome. So I do want to make sure that everyone has this page taken down, either in notes or a picture. Stop the lecture.